Hi, this is Patel. In this lecture, we are going to look at the advanced version of the strain energy that has been stored in the body due to the shear stress. So this is very important concept using which similar type of the strain energy stored in the body due to the bending stress or due to bending can also be understood. So basically strain energy is a part of strained that the energy that has been stored in the material due to the straining. So it could be any type of a straining due to the shear stress, due to the impact loading, gradual or the sudden loading, or due to the bending. Material can bend or it can be strained using any type of the load. We have seen many type of the loading condition in the previous lecture. We have started with the gradually applied load, then we have seen the suddenly applied load. After that we have seen impact load, and we have seen that in our day-to-day life or the practical life it is not compulsory that the loading condition is gradually applied load, which we have assumed till in previous chapters, in which we have taken that assumption that all the loads are gradually applied load, which is not perfectly true in the working conditions. So we are going to look at the shear stress condition in this particular lecture. So you will see that here is the theory of strain energy stored in the body due to the shear stress. We know that shearing always occurs layer by layer. So whenever we are talking about the shear stress energy, the body will try to shear in this manner. It will try to slide on upper layer. Sliding upper layer would be on the bottom layer. So the diagram itself indicates that this is the original condition D point, and its new point is D1. Similarly, it was here at C point, and after applying the shear stress or shear force, its new position is C1. Now below points are A and B, both are fixed at this particular surface, so they are not allowed to slide on anything else. As you go upward in this direction, then you will see that the shearing amount or the shearing effect intensifies. It increases from the height, from the amount of the height from the base. So consider the cube ABCD of the length L fixed at the bottom face AB as shown in a figure. So the P force is applied tangentially on the face DC. So we are applying the P force tangentially, and tangential direction itself indicates that it will create the shear stress. Tau is our shear stress, phi is our shear strain, and N is modulus of rigidity or shear modulus. We know that N is nothing but stress upon strain. N is nothing but stress, that is tau, divided by strain, that is phi. We have already studied this type of a elastic constant in the previous lectures. This was just a quick reminder so that you guys can understand it. Now if the force P is applied gradually, then the average force would be P by 2, because initially there would be a zero amount of the force applied in the first second. Then after the force amount will increase to up to the maximum value P. So the average value would be the 0 plus P divided by 2, which will give us the answer of the average force, that is nothing but the P by 2. Now what is the work done? Because here in the entire chapter we have seen that strain energy can be calculated by comparing it with the work done. So work done is our first agenda that we need to find out here. So the work done is average force divided into distance. We know that the average force is nothing but the P by 2. Distance is now D into D1, or we can say that D1. Why is it so? Because this is the distance traveled by the upper surface due to the sliding. So this distance is very important to find out the work done. So we know that 1 by 2 into P as it is, and instead of the dd1, we have seen that dd1 can be written as AD into phi. Actually, this phi angle is very small, and if you notice, AD is the adjacent side, dd1 is opposite side. So if you find out the tan theta, so tan phi is nothing but the opposite upon adjacent. So dd1 can be calculated as the AD into tan phi. But here angle is very small, so tan phi can be written as the phi. That is why we have written AD into phi instead of dd1. This is very basic geometry as well trigonometry, and using which we are further calculating that instead of P, we can write stress into area. What is the amount of stress? That is tau, and area is dc on which it is applied. Now instead of calculating the converting this point, we are keeping this AD into phi as it is. We know that phi and tau are both related, because we already seen that modulus of rigidity is equals to shear stress upon shear strain. So instead of writing this, we can write in terms of the phi equals to tau upon n. So instead of phi, we are going to write it as a tau upon n, and the rest of the thing will give us the answer of volume. So we can convert it in terms of the volume. So this is our equation till now. Now if we simplify this equation further, then we will see that u is nothing but tau square upon 2n into v, where we have seen that n is nothing but the modulus of rigidity. We also know that the modulus of resilience is equals to strain energy per unit volume. So the strain energy is containing the volume V. If you divide this by the volume, you will get the strain modulus of resilience as tau square upon 2n. So these are the basic terminologies and the equation that you need to keep in your mind while solving the example, so that you guys don't get confused with the equation, because there are a number of equations as per the cases, and according to cases you have to pick one right equation in order to solve the example. So here a rectangular body of 500 mm long, 100 mm width and 50 mm thickness is subjected to a shear stress of 80 megapascal. So basically they have provided us the dimension of the body as well as the shear stress of 80 megapascal. Determine the strain energy stored in the body. So we are required to find out the strain energy stored in the body. Take n equals to 85 gigapascal. So this is how we have seen that to identify this type of example is the first sign is that they have asked you to find out the strain energy. Second thing, instead of any kind of a load, they have mentioned it that the body is subjected to a shear stress. So basically this is the case of the shear stress where the energy is to be stored in the body, and that particular energy is required to be calculated. So now if you list out all the values, then the length of the rectangular body is 500, width is nothing but 100, next thickness is nothing but 50, shear stress is 80 megapascal. That can be written as 80 into 10 Newton per mm square. Modulus of rigidity is also written in terms of Newton per mm square. First things that we are going to do is to find out the volume, because all the dimensions are given. All you have to do is to insert those dimensions into this equation and calculate using the calculator to get the answer as 2.5 into 10 raised to 6 mm cube. So this is our basic answer. Again, the strain energy stored in the body is asked here. So we required to find out the strain energy. We know that the equation due to the strain energy generated due to the shear stress is nothing but the tau square upon 2n into V. I would like to clarify one thing, that n is modulus of rigidity or modulus of stiffness. So this particular modulus of rigidity is represented by C and G also. So in some of the reference book, they might be using the symbol as the G or C. So don't get confused book wise. You just have to insert all the value into this equation, and that will give you the answer in terms of Newton into mm. So convert this answer, or you can leave that particular answer as it is both valid. So you can put the answer in terms of Newton into mm, or either you can convert it into Newton into meter or kilonewton into meter. So this is up to you. In examination they will not cut your marks based on this. So this was the example based on the shear stress. In the further studies, you will see that the strain energy examples are generally used or asked in competitive exams. So in those exams, you need to remember these equations thoroughly so that you can put the values into them and get the answer required in the minimum time. So I recommend all of you to list down each and every equation that we have derived and practice them one by one, so that you guys can solve any question, whether it is a MCQ or numerical or example. You can easily solve those particular things. So we conclude our lecture over here. Till then, thank you.